Okay, so here we've got the notes for section 5.3, which deals with estimating a population mean. So the first case we have here is the case in which you do not know the population standard deviation. So it's an unknown value. So in the previous sections, we've known this value of sigma for the whole population. So because of that, we actually can't use our z-table. We need another table, which is referred to as a t-table instead. So just some definitions. So population mean, sample mean, number of sample values, and margin of error. So these things are all the same as if we had a normal distribution. Some requirements. We have a simple random sample. The population is is normally distributed, we know it, or the population is more than 30. So it doesn't have to be normally distributed if you have more than 30 people. So confidence interval notations, so the sample average plus the error minus the error, the mean will lie somewhere in between there, or you can write as plus minus or as the interval notation. Now, since we don't know sigma, we can't use our z-table, so we have this different formula for E. So T alpha over 2, so this is from the t-table. S is the sample standard deviation, so be careful, it's not the population. And then square root of n, where n is the number of measurements we made. So T alpha over 2 is similar to Z alpha over 2, but we'll talk about it when we look at the table. So just some rules for rounding off. You always round to one extra decimal place. So if you have this, you can round to the same number of decimal places. I'm not going to be too terribly concerned about the rounding errors. Okay, so that brings us over here to the t distribution. So this equation gives us a value of t-score instead of a z-score because we do not know the standard deviation, so we can't use the actual formula anymore. Except there's a typo in this equation. This x should be an s instead of a sigma. So be careful with that. So down here it talks about the degrees of freedom. So degrees of freedom is always one less than the number of measurements you make. Essentially, we kind of talked this a long time ago, where if you have a random set of test scores and you want your average to come out to be a certain specific value, you can randomly assign, so you have 10 test scores, you can randomly assign 9 of those test scores to be whatever you want. But that 10th one, if you've randomly assigned the previous 9, has to be one specific value. So the degrees of freedom essentially is how many can you randomly select before the last one must have a specific value. Like if I want my average to be 80, I can't put 10 random test scores in. I can put 9 random test scores in, but then I'd have to do some math to calculate what that 10th score would have to be in order to make my number come out to be the grade that I want. Okay, so example 1, a sample size of n equals 12 is a simple random sample selected from a normally distributed population, so we meet our criteria. Find the critical value t alpha over 2 corresponding to a 95% confidence interval. So now remember, alpha is the amount more than, and then we divide by 2. So essentially you're taking 1 minus 0.95, which is 0.05, and dividing it by 2, so 0.025. So if you think about your curve, you've got the bell-looking shape, and in each of these regions, I have 0.025. Now, the t-table looks like this guy. If you notice, there's 2 different headings, area in one tail versus area in 2 tails. So we're using an alpha over 2, we're using 2 tails. So in one tail, in each individual tail, I have 0.025. Or the total area down here, the area in 2 tails would be if I added that piece up and that piece up, be the 0.05. So you notice this value here is always double this one. Because if there's 0.05 in one tail, that's the same on the top and bottom, adding up to a total of 0.1. So here's how you read this table. So we're using this column, because either of these numbers works, and our degrees of freedom is always 1 less than our n value. So our n is 12, so I'm going to go down to row 11 and read across, so 2.201. So our critical value, t alpha over 2 is 2.201. So that's how you use that t-table. All right, so here, just some work for finding critical values, or then confidence intervals. So we'll have to find our critical value first, then we'll use this equation. S is the sample standard deviation, N is the number of measurements, and then we'll add or subtract it from our various values. So if you look at example 2 here, said listed below are speeds in miles per hour measured from southbound traffic on I-280 near Cupertino, California. So simple random sample. The speed limit is 95. Use a sample, construct a 95% confidence interval. What does this confidence interval suggest about the speed limit? So what we need to do first is we need to calculate our average and all of those other measurements that we need. So I actually already entered these guys into my calculator because it will tell me it's this column right here. It's my list 1. So from this, so X bar is my average. We'll jot that guy down. 60 point, we'll call it 7. And now if you look down here on my calculator, I actually have 2 standard deviations. There's sigma and there's S. So sigma would be if there were only, how many are there? 12. So we'll jot that down. There's 12 cars. If there are only 12 cars in the world, I've measured the population. I measured every car that drove down that road. But that's not the case. So I can't use sigma. I have to use S because I didn't clock every car. I clocked a sample of them. So S is 4.1. So those are the numbers that I need for my formula. So since N is 12, we need one other thing. We need our t-value. Now, I'm not going to look it up again, but since we're doing a 95% confidence interval and we have 12 measurements, that's actually the same thing from example 1. So our t-value is 2.201. So the formula for the error is our t-value times the value for S, 4.1, divided by the square root of N. So it'd look like that. And then if I math that out, menu 2.201 times 4.1 divided by root 12 gives an error value of 2.6, we'll call it 1. So 2.61. So let's see here, use the sample data, so we need to construct the confidence interval. So the confidence interval is going to have mu in the middle. On the top, we're going to have our average speed plus the error. And on the bottom, we're going to have our average speed minus the error. And then we work that math out. And 60.7 minus 2.61 is, we'll call that 58.1. And 60.7 plus 2.61, 63.3. So if the speed limit is 65, our drivers are going under the speed limit because 65 is more than our maximum value, including the error. So there are some speeders. So on average, we'll put it that way, people are not speeding because up here, obviously, that person is speeding, that person's speeding. But they are outliers. All right, example 3. So we got 12, again, tells us in the direction, so our N value is 12. The time in seconds of alcohol usage recorded with times listed below. The study justifies the assumption that the sample can be treated as a simple random sample, so criteria 1's met. Now, there is one problem with this, is that if you look at these numbers, there's a bunch that are very, very small, 0, 43, 0, 2, 57, 50, 14. These are all less than 100. And then you have a couple very, very large numbers. So what that means, if I did a histogram, these would not be normally distributed. So that second criteria where it's a normal distribution or I have more than 30 measurements, that fails. So this one actually cannot be done. The data does not meet the criteria. It has to be normally distributed or more than 30 measurements, and neither of those two things are true. I have a bunch of very, very small values and a couple very, very large values. So the histogram, or if you plotted the curve, it actually looks something like this. A lot of very small values, nothing in the middle, and a couple very large values. So I can't actually do this problem. All right, point estimates, we've talked about these before. So to estimate the average, you add the the bounds, divide by 2. The error is the difference, divide by 2. So let's see here. Example 4, 95% confidence interval was constructed based on accounts of chocolate chips and 32 Chips Ahoy cookies. Limits were found to be 18.128 and 20.06. Find the values of the best point estimate x bar and the margin of error. So x bar is the sum divided by 2, and E is the difference divided by 2. So for the sum, 20.06 plus 18.128 divided by 2, so that's going to be 19.09. And down here, the error, 20.06 minus 18.128 divided by 2. This is 0.966. So those are our values for that. All right, down here, we've got the formula to work backwards. How many measurements do you need to make to have a given confidence interval? So once again, we have our alpha over 2 value here. Some definitions: mu is the population mean, sigma is the population standard deviation, x bar is the sample mean, so the average of our group, E is our margin of error, and z alpha over 2 is our confidence interval. So the round off rule, be careful here, is you always round up. So even if it's 0.00001, it rounds up to the next number, because you have to have at least the number calculated. So always round up. All right, so example 5. Assume we want to estimate the mean IQ scores, the population of STAT students. How many students must be randomly selected for IQ tests if you want a 95% confidence interval, and the sample mean is within 3 IQ points. So n is equal to, so from our previous notes, the z alpha over 2 for 95% is 1.96. So essentially what you'd have to do is you would take 1 minus 0.95 and get 0.05, divide that by 2, 0.025, and look for that value in your z table, since that's a z-score. So let's see here. Times the standard deviation, which is 15, it's given to us in the problem. And then I want to have 3 points worth of margin of error, so, and all this goes in my calculator, 1.96 times 15 divided by 3, all that squared, which comes out to be 96.04. But I can't have 04 people, so this rounds up to I need to survey 95, I went down, 97 people in order to make sure that I'm within 3 points from my margin of error. So this last thing we have here is if we do actually know sigma. So if we know sigma, we can use this equation. Instead of t, it becomes z, and instead of s, it becomes sigma. So t is used if you have a sample, z is used if you have the whole population measurements. All right, so use a sample 12. So this is the same measurements we had before from the highway speed problem. So I'm going to pull that data up again. So our n is 12. So, sorry, I'm using this equation, z alpha over 2 times sigma over root n. So there's our n. Sigma is given to us as 4.1, and our z value for 95% is 1.96. So to be honest, you should probably just memorize that because 95% shows up a lot. So knowing it, the z value is very, very handy. So the error is z value times sigma over root n. If you notice, this is very similar. The only difference is when we were doing this with t, the number was different. So 1.96 times 4.1 divided by the square root of 12. This error comes out to be 2.32. So construct the confidence interval. So the average, I should have jotted that down because that's what the confidence interval is based off of. So the average measurement was, 60.6. So in this case, is going to be 60.6 plus that. So 60.6 plus 2.32. If I can type in my calculator right. So this is 62.9 miles per hour, and on the bottom, 60.6 minus 2.32. So that is 58.3. So that would be my 95% confidence interval if I knew the standard deviation. And if you notice, so here's our numbers. Whoops, where'd it go? When you had t, so 58.1 to 63.3, this is 58.3 to 62.9. So if you know the population values, your confidence intervals will tend to be slightly more narrow than if you use the t, because the t is kind of an approximation, so it leaves a little bit more error built into the equation already. So knowing sigma is better than not, but you can do it if you don't by using the t distribution. And then down here at the bottom, we've just got how you choose the correct one to use. So if you do not know the population standard deviation, and is normally distributed, or you know more than 30, you use the t. If you do know the population standard deviation, if you are given sigma, then you use the normal or the z distribution. So that's how to tell which table you should be looking in. If it says sigma equals, use the z table. If it says s equals, use the t table. But that brings us to the end of this section.